thanks to the organizers for picking up this particular talk as a soft transition from science policy and management to hard science. And this decision has some reason behind. The project motivation is actually very simple. All what we are doing is basically about how much you can see if you look properly at sea surface. So what I'm going to present is results of 8 teams from 5 countries targeted to a very simple application, a very simple thing, how to keep our coasts clean. A major oil pollution is a Albtraum for any coastal country, and they did happen sometimes, and the question is whether we can do something about that. There are many people who are addressing one component of risk of having polluted your coast by oil, and contemporary understanding of risk, starting from Van Dantzig's time, which is only 50 years ago, is that risk is a product of probability of accident and cost of consequences. So what we were trying to do, we were trying to reduce the consequences of disasters, what might happen on offshore. And the idea is simple. We can't drive the winds, we can't drive the currents, we can't drive the waves, but we can adjust the location of our activities so that if something bad happens, then the pollution will not reach the coast. If it does happen on offshore, it is bad, but when the pollution comes to the coast, that's a disaster. So the method we picked up for solving this problem is actually methods for solving inverse problems. So we were aiming at quantification of offshore areas, which is something like maritime spatial planning. So quantification in terms of their ability to supply coastal pollution through current-driven transport. For doing that, there are no simple ways, but there is a simple logic. It's necessary to pick up, if possible, the best existing circulation models for the sea, because everything what happens to the sea surface here is driven by 3-dimensional currents which happen sometimes in the water mass, and you have to know all that in order to understand what happens with surface current-driven transport of things. The second step towards the goal is that you have to make clear the subtle difference between Euler and Lagrangian velocities and transport. It is necessary to calculate how some substance which is thrown into sea surface actually propagates, which is possible to do with contemporary models. As a result, it is possible to get a new map of the sea. It is not a map of salinity or density or depth. It's a map of environmental risk in terms of probability of hitting the coast by pollution put into different points of the Gulf of Finland. And based on those maps, the last step is actually not the least, but actually not very hard in terms of science, but hard in terms of explanations, decision making. It's necessary to make some sense out of those maps and to create sort of practical ways of practical using of those maps. And one simple application is to try to find out a globally optimum fairway in terms of minimizing the probability of hitting the coast by pollution which accidentally or by whatever reasons will be created along the fairway, or to try to maximize the time it takes for the pollution to reach the coast. The typical result in Gulf of Finland conditions is that the ship owner loses in about 5% in sailing distance. So you have to sail about 5% longer. But it is possible to reduce the probability of coastal pollution by up to 1/3. And it's possible to increase the time what you have to combat the pollution about 2 to 4 days. So this is by up to 50%. And of course, additionally to that, it gives some contribution to maritime spatial planning, because what comes out is that the sea areas with seemingly similar geometry and hydrography have completely different internal properties in terms of surface current-induced transport. The essence of this exercise can be explained in, or said in quite simple terms. So we have actually developed a prototype of really green environmental management technology, which doesn't need much investments. It's about how to properly sail, or how to properly organize our activities in open sea. The trick is that we have used the approach of inverse problems. And the gain can be measured either in terms of time to react to the pollution, or in terms of lower probability of having hit by pollution to the coast, or by much more detailed understanding of how exactly the marine dynamical system works. So the key outcome is not exactly to determine how the ships should go, but much more importantly, to understand that the value of offshore areas in some terms is different. The offshore is not homogeneous, it's very much heterogeneous. And contribution of this exercise to science and management can be formulated in different terms. We have developed a technique for environmental management, sort of applications for finding safe airways. We have made clear some properties of surface currents with the use of experiments first ever done in the Baltic Sea area. So we're really happy about driving both science and management. Thank you.
Thank you. And